Hi, good afternoon. I'm Gavin Jones. I'm a Senior Application Engineer with SmartUQ. And today I'm going to be presenting the webinar Predictive Analytics for Simulation, coupling SmartUQ's Analytics Toolset with Adam's Car. Before I get started, I'd like to give a little bit of background on SmartUQ and who we are as a company. We're a predictive analytics and uncertainty quantification software and consulting company. It's based in Madison, Wisconsin. Our primary product is our software package, SmartUQ, which is going to be used throughout this presentation. We're going to illustrate the use of SmartUQ in conjunction with Adam's Car, and you can see some screenshots on the right there that illustrate SmartUQ and visualizations that are present in the software. Overall, our mission is to deliver innovative software solutions that solve difficult problems in engineering and industrial applications. And we have customers across a wide range of industries in different roles, including engineering, testing, and analysis groups. The agenda for today's presentation, we're going to begin with an overview of predictive analytics and uncertainty quantification. Then we're going to discuss specifically SmartUQ's predictive analytics and uncertainty quantification workflow. And we'll discuss the benefits of uncertainty quantification to engineering analysis. Next, we'll present how SmartUQ and Adam's Car interface together and how the workflow using the two of them in conjunction can be leveraged to perform engineering analyses. And we'll conclude with a fishhook simulation example that's going to demonstrate that workflow. And with the remaining time, we'll have questions. So I'll begin with the definition of predictive analytics. Predictive analytics encompasses a set of statistical tools used to analyze and extract information from data for the purpose of developing predictive models. And a key use of predictive models is in uncertainty quantification, which is defined by the NAFM Stochastic Working Group, and ASME V&V10 is the formulation of a statistical model to characterize imperfect and/or unknown information in engineering simulation and physical testing for predictions and decision making. So if we look at the diagram in the upper right-hand corner, we could consider, for example, a component that's designed to meet some specific criteria. It could be strength, for example. In the traditional approaches, we basically assume that all manufactured and deployed components are going to possess that exact nominal strength value, and decisions are made accordingly throughout the life cycle of the component. However, uncertainty quantification is going to take the view that the strength of actual produced components differs from that nominal value due, for example, to manufacturing uncertainties and differences in the operating environment. The ultimate objective is we want to quantify that performance variation and its effect on downstream quantities of interest. That is, we want to answer the question of how likely are certain outcomes if some aspects of the complex system are not exactly known, so that we can design from the start with that information in mind. Doing so is going to save time and cost across all phases of the component's life cycle, and it's going to also allow for better design and improved performance. In simulation, the uncertainties we face can come from uncertainty in system inputs, such as the initial conditions or boundary conditions. Further, we know that all models, no matter how detailed, are approximations of reality, which introduces uncertainty due to the assumptions and simplifications made in constructing the model. Solving the model ultimately is going to introduce computational numerical uncertainties. That could be, for example, due to discretization error. And lastly, it's often the case that we want to tune the simulation model parameters to better match real world or experimental data. And so we must be aware of the uncertainties present in physical testing. Those uncertainties could arise from experimental error or instrument precision, for example. So what then is the benefit of having access to probability distributions of outcomes and accounting for uncertainties? Uncertainty in engineering analyses has typically been handled using design margins. So for some specific loading condition, the component gets designed to have a strength that meets that loading condition, and then some additional factor of safety is added on top. The additional factor of safety is typically determined using historical precedent or engineering judgment or a combination of those. However, if we consider there to be uncertainty in the loading, we see that in some cases the load is going to exceed the strength and the component will fail. Now, whether or not this is a problem, of course, depends on the specific situation and the costs associated with failure of the component. But the main point is that we now have quantifiable information that we can use to make better, more confident, more informed engineering decisions. We could go a step further and consider uncertainties in the component's strength. And now we see there's an even greater probability of the load exceeding the strength and that the component fails. And now it becomes less likely this is something we're willing to accept. We can't accept this greater level of risk. Often in practice, though, what we do see is the opposite situation, that when the uncertainties are understood, it's revealed that the more deterministic approach utilizing design margins was too conservative, and we actually have room to tighten the design margin. That is, what we tend to see in practice is rather than an overlapping of the distributions, we see the distributions are spread too far apart, and as a result, we can make decisions to bring those distributions closer together. So how does SmartUQ fit into everything that's been discussed to this point? To answer that question, I'd like to present sort of a basic workflow of predictive analytics in UQ that SmartUQ tools are used for. The real end goal is that we want to get to step 5 in this diagram. So we want to be able to thoroughly explore our design space or perform sensitivity analyses to understand how the inputs to our system and changes in those affect the outputs. Or we want to perform an uncertainty propagation where we take uncertainty in our system inputs and try to understand how that uncertainty propagates through the system and results in uncertainty in the outputs we're looking at. We might also want to perform optimization algorithms. One thing that everything in step 5 has in common, though, is that it all requires a large number of evaluations of the underlying system, or in this case, the simulation model that we have. And for a lot of cases, a simulation model might take hours, even days in some cases to run, and it becomes computationally too intensive to take a direct approach of running simulations directly to perform these tasks. So you might not be able to afford to run a large Monte Carlo sample to perform an uncertainty propagation because you can't afford to do 10,000, 20,000, 30,000 runs of a simulation model that takes an hour to run each time. Similarly, you might not be able to afford the number of simulations required to have your optimization algorithm converge. So where SmartUQ comes into play is in creating an emulator or statistical model that looks to act as a surrogate for this simulation model. So essentially, we build a statistical model that maps the input-output relationship of the simulation model, and then we use that emulator model in lieu of the simulation to perform these high-volume sampling tasks. Another aspect of SmartUQ tools is designs of experiments and data sampling. So in this portion of the workflow, we're ultimately selecting which points we want to run in the simulation model in order to collect the training data to actually build this emulator. And the design of experiment tools we have are set up and selected such that we're efficiently collecting this data. So that means that we're collecting the minimum amount of data, running the minimum number of simulations to achieve a desired accuracy in our emulator. And we can also, as I alluded to before, conduct statistical calibration. So in that case, we might want to tune parameters within our complex model to better match physical experiments or physical data we've collected. And that's something as well that can be a part of the SmartUQ workflow. I'd like to take a brief minute then to discuss what the ROI is of predictive analytics in UQ. So the application of SmartUQ tools for predictive analytics in UQ can save time throughout the product lifecycle. The ability to more thoroughly explore the design space using a predictive model in place of the full fidelity simulation runs allows for more problems to be caught earlier in the design cycle, preventing time-consuming and unnecessary design iterations. Understanding uncertainties and risk saves time by avoiding going too far along a path likely to result in failure and a required redesign. And understanding the relative importance of input parameters through a sensitivity analysis, for example, can simplify future simulations. In general, those time savings achieved are going to directly translate to cost savings. So for example, avoiding unnecessary prototype and test iterations by addressing issues early in the design phase through predictive modeling and analytics removes the large costs associated with conducting unnecessary tests and building additional physical prototypes. Calibration utilizing predictive models can also be used to validate that simulation results agree with physical data. Understanding uncertainty and therefore risk can lead to decisions that maximize product reliability. Many governmental agencies and professional organizations have also begun producing requirements and best practices for simulation modeling and validation that require an ability to perform tasks such as quantifying uncertainties and understanding the sensitivity of quantities of interest on key model parameters. And further, as simulation becomes more complex and their use becomes even more widespread, the push towards quantifiable model validation is only going to grow stronger. And SmartUQ is a user-friendly, robust tool that can fill that need. So now I'd like to discuss a bit on the integration of SmartUQ and Adams Car, so how you're going to access Adams Car from SmartUQ to execute some of these workflows. So essentially, the process begins with the user selecting the Adams Car assembly and experiment that they'd like to study from within SmartUQ. And then SmartUQ is going to call out and query the Adams Car session for all the available candidate factors and objectives, so all the available inputs and outputs for that experiment. And then within that large list of potential factors and objectives, in SmartUQ, the user can search and select the specific factors and objectives that they're interested in using in their study. Now, once SmartUQ has those factors and objectives, you can set bounds for those factors. You can create a DOE within SmartUQ of those factors, and then you can directly send from SmartUQ to Adams Car the DOE so that Adams Car will run the simulations directly that the DOE is prescribing. Once all the simulations have been completed, Adams Car is going to then send the results back to SmartUQ. And from that point, you have the DOE in SmartUQ, you have the results of the simulations that correspond to that DOE in SmartUQ, and that's where you can start directly applying the SmartUQ tools to build emulators and perform analytics to perform your engineering analyses. So next we'll move into an example that is going to tie everything we've discussed to this point together. The example is a fishhook simulation in Adams Car. The test begins with the vehicle driving directly forward at 60 kilometers per hour. The steering wheel then gets turned 90 degrees to the left and held for 0.65 seconds. The wheel then is turned 180 degrees to the right of neutral and gets held for 3.5 seconds. And the responses that get measured, or the outputs of this simulation, are the maximum roll angle, the maximum steering angle, and the maximum yaw rate throughout that maneuver. And we can take a look at the simulation itself here. So again, the simulation is producing an output of roll angle, steering angle, and yaw rate, and then we pick out specifically the maximum value of each of those during the course of the maneuver. There's 10 design parameters that are going to get varied in this study. So the first 9 parameters are geometric related parameters. So we're looking here at the rear suspension system of the model, and we have 3 points circled in red. And with each of those 3 points, there's an X, Y, Z coordinate position we can manipulate. And so those are the 9 design parameters we're looking at, the X, Y, Z coordinate for each of those 3 points. And the bounds within which we allow that to vary, so we allow our design to have bounds within, is plus or minus 30 millimeters from the nominal design location. So that would represent the DOE bounds for those coordinate positions. The last design parameter we have is the mass of the vehicle's chassis, and that has bounds between 950 and 1,050 kilograms. So these are the 10 factors that we're going to ultimately ask. SmartUQ is ultimately going to ask Adam's car for. We're going to build the DOE across these parameters, and then we're going to ask Adam's car to run these simulations for us. So before we move into more of a demonstration of how this is all going to work, I want to take a moment to review the workflow and how things are going to proceed. In our first step, in our design of experiments step, this is where SmartUQ is going to go out and ask Adam's car for the list of inputs and possible outputs. We're going to select amongst those the inputs and outputs we're interested in studying for this example. Then using that information, we're going to create a design of experiments in SmartUQ. We're going to have SmartUQ ask Adam's car to run those simulations, and then Adam's car is going to send back to SmartUQ the results of the simulations. And then we take that information in the next step, and we use it to train our emulator or our surrogate model within SmartUQ. Then using that model, we can very quickly do an optimization. We can, in this example, we're going to optimize to minimize the roll angle and the yaw rate. So it's going to be an optimization with multi-objectives. We're also going to want to verify that the SmartUQ prediction at the optimum solution agrees with what an Adam's car direct simulation would produce. So we'll do that as well. And then once that's been done, we're going to move on to an uncertainty propagation around the optimal design. So the idea here being that through our optimization, we've determined the design we'd like to use for the chassis that we're going to be producing for the suspension systems. But when we actually go out into the real world and start manufacturing these chassis, we're going to get some variability due to, for example, our manufacturing processes. So we're not always going to produce exactly the optimum solution. So we want to understand, given what we know about the uncertainty in our manufacturing process, what sort of uncertainty are we going to see in the output? So how close are we going to be to the output, the optimum output that we achieved in this optimization, given uncertainty in those system inputs? And we're going to use that information to decide whether we need to make adjustments to our manufacturing process so that we're meeting our requirements a sufficient amount of the time. So here we'll start with looking at a video showing the first phase, the interaction between Adam's car and SmartUQ to, first of all, bring the information into SmartUQ about the study and the experiment, and then create the design of experiments and ask Adam's car to run those simulations for us. So one thing is that you're going to want, as part of this process, to have the Adams command server running in order that SmartUQ can interface with it. And then we'll see that in SmartUQ, the server address and port number are going to auto-populate with their default values. And now we're going to show starting up the command server. And this is what's going to allow us to retrieve events from Adam's car. And we can select the event we're interested in and then use that to retrieve experiment. So doing this is going to bring back, the full list of parameters and objectives from Adam's car. But we can search in SmartUQ amongst those parameters and objectives to find the ones that we're specifically interested in for our study. So we're looking for those 10 design parameters we're going to be modifying, and then the 3 maximum output values that we wanted to look at. So, and now we see that information pulled into SmartUQ with the lower and upper bounds from Adam's car. And we can just directly copy this information to the clipboard and then use that to create our DOE in SmartUQ. So we're going to do 100 runs across those 10 factors. And here we'll just paste in the bounds information directly. And we can also edit these lower and upper bounds. We want to edit these to be within the bounds we defined in our problem statement. And we'll go ahead and just paste in all of the correct bounds here for that. And then we can click Generate LHD to actually produce that design of experiments. We see we have one row for each simulation we're going to run. And we can look at the visualization of that input space for the design of experiments and see that it's very space filling. And now we will directly run that design of experiments from SmartUQ. So we'll select prediction, and then the design of experiments and predict. And now SmartUQ is calling out to Adam's car to run those 100 simulations in that design of experiments. So we won't sit and watch the 100 simulations run here, but once all those simulations have completed running, all the results will get sent from Adam's car back to SmartUQ so that we can use them in the next phase of the process. So in that next phase, that's where we're taking the design of experiments and the results at those points from Adam's car, training our emulator, and then using that emulator to optimize to minimize the roll angle and the yaw rate, minimize the maximum roll angle and the maximum yaw rate. So I'll switch over to SmartUQ to demonstrate this portion. So for our inputs to the system, we're going to have the optimal LHD that we created. And then for our outputs, we're going to have the predictions that were sent back from Adam's car. And then we have a number of settings we can select from when building this emulator. But for the most part, this is a fairly hands-off portion from a user perspective. And most of our models are going to build very quickly. So we even have a tool that's going to try all the different combinations of these settings, build a model for each, produce a report that shows the accuracy for each of those, and then that allows you to sort of select the settings based on that brute force approach. Here for this example, just use the default setting, so I'm going to click Generate Emulator. And the first screen we get here is showing us an assessment of the accuracy of our emulator's predictive ability. So the way to think about this plot is you could imagine, well, first, each of these points on the plot represents one of the training points we use, so one of the 100 points from our design of experiments. But you can imagine from those 100 points, you could pick one of these points. So say, for example, this one. You could remove that from the training set, so then you'd be left with 99 total points. You could use those 99 points to build an emulator. And so from the perspective of that emulator, this point that we're looking at here that was removed from the set would be an independent validation point. You could then use the emulator to predict the value of this point. That corresponds to the x-axis value. And then the y-axis value would be the actual value of this point. But you could then imagine if you repeated that process across all 100 points, you'd get a plot that looks like this. And if every prediction matched exactly, all the points would be along this y equals x line. And essentially, we measure the accuracy of the emulator as being a best fit of the points to this line, which is this CV error And then the standardized CV error is done in order to compare across outputs that have different magnitudes. So this is computed by dividing the CV error by the standard deviation of the outputs from the training set for that particular output. So here this is under the point 0.1 here is a pretty accurate emulator. And we're going to go take a look at some of the other options we have to visualize this emulator. So the first is a surface plot. So this allows you to visualize how the output varies with respect to two separate inputs. A very useful view we have is this multi-view feature. So in this multi-view, we can see not only local sensitivity, but we can also start to get a sense of how various inputs interact with each other to affect the output. So the local sensitivity aspect is looking at, so for example, the inputs are along the top here, the outputs are on the left. So when we look here, we can see from the slope of this line that as we increase the value of this input, we're also increasing the value of this output. But we'll also notice that as we adjust some of these, as we change where we are in the design space, we're going to see the slopes and the shape of the lines in other plots change as well. And that's a sign of the interaction effects between those inputs. So if we look at input 1, output 3, we can see that there's a linear relationship here, but as I increase the value of this input, the output decreases. But if I go and change where I am in the design space with respect to this input, and I put it to a low value, now we see that there's a linear relationship still, but it's the opposite. So now when we increase the value of this input, we're also increasing the value of the output. We can also start to get a sense of some of the uncertainty propagation power within SmartUQ from this view. So on the right side here, we're seeing a histogram that represents the outputs of here 500 predictions according to these input distributions along the bottom. But we could adjust the shape of these distributions, for example, and then we see the histograms update. And to get a sense of how quickly the predictions are being made, I can change this to 50,000 predictions. So we're going to draw 50,000 points from these distributions, and we'll see how quickly the output distributions update. There we go. So very quickly. So with our emulator on this next steps tab, we can see the various tasks we can undertake. So we could do a validation. So for example, if we had additional simulation runs we performed that we didn't use to train the emulator, we could predict the value of those as a measure of accuracy of the emulator and compare with the actual values. We could do direct predictions. We could do optimization, sensitivity analysis, or uncertainty propagation. So in this example, we're going to want to start with that optimization. So we have a section here where we can, if we want to constrain the bounds within which the optimization is occurring, we can do that. We can also set further constraints directly within this Python text entry box. And the goal of our optimization, if we recall, is we want to minimize the maximum roll angle, and we also want to minimize the maximum yaw rate. If we leave our objectives type set to individual, this is going to actually perform two separate optimizations, which is not what we want. It would perform one optimization to minimize this value and one optimization to minimize that value. So we actually want to do a combined There's a couple methods across which by default we can select how we average, how we combine these objectives together. And we can set weightings on those to determine which of these objectives is more important than the other. Or if we want more flexibility versus these pre-built options, we can use user-defined function in Python. So within this text box, you can define your own objective for combining the optimizations together. So there's a lot of flexibility here. But for this example, we're just going to use the default. We're just going to use the combined and the geometric averaging. And we have a number of different optimization algorithms that can be used, but we'll use the default for that as well. So the optimization is complete, and we get the solution here. So the first 10 columns are going to be the inputs that correspond to the optimized solution. And then these next 3 columns are going to be the outputs that we get for that optimization. So these are SmartUQ's predictions for these outputs given these inputs that we found as the optimal solution. So we'll switch back to the slides here to see the next phase. So this is where we're going to want to verify in Adam's car our optimum solution. So we want to make sure that when SmartUQ is telling us that at this solution I found is an optimum, these are the outputs, that when we run those that optimized solution directly in Adam's car, that there's agreement in the outputs that Adam's car produces with the predictions that SmartUQ made. So here we're seeing what I just showed in SmartUQ, so the result of the optimization process. And this is a file, remember, in SmartUQ, so we can access it directly when we do the prediction. So here we select the optimization. We select the first 10 columns of that because those are the inputs. And that's going to ask Adam's car to run the simulation at those points. It's doing that right now, and then once it completes this process, it's going to go ahead and send the solution back to SmartUQ, which is what it's doing now. And we now see those values. So we can go ahead, for comparison's sake here, to see how well things went. We can copy those values out. So this is the direct results from the Adam's car simulation. And then we'll go to our SmartUQ optimization and look at the outputs that were predicted. And we can see there's very good agreement. So in the worst case, it's still less than 2% error. So the last step in our example here is uncertainty propagation around that optimal design point. So now that we know what the optimal geometry and optimal mass is for that chassis, we'd like to know how uncertainty in those values when we actually go to produce these chassis is going to affect our uncertainty in our maximum roll angle and our maximum yaw rate. So I'll switch back to SmartUQ to go through that process. So I'll go to the next steps tab in SmartUQ and I'll select uncertainty propagation. And so we have a table here showing all of our different inputs. For each of those, we can select the distribution that characterizes it. And when we select a distribution, we can adjust the parameters that further define that distribution. So here, what we're going to do is we're going to select normal distributions for everything. We're going to assume for the geometric parameters, so the parameters that define the XYZ coordinate positions, that everything has a mean of the optimized value, so the mean of the solution our optimization found, and that the standard deviation about that mean is 0.25% of that of the mean value. For the mass, we're going to do it a little differently. We're still going to assume a normal distribution with a mean equal to the optimized solution, but we're going to assume that the variability about that mean is 1% of the mean value. So I'll go and directly just copy in results for those values. And then we can set here how many samples we want to take. So I'll do 100,000 samples. So we'll select from this grouping of distributions 100,000 times, and then we'll make predictions on those, and we'll see what the output distribution is that we obtain. So here's our output distribution for the maximum roll angle. And we also have a distribution for the maximum yaw rate. We can adjust the number of bins in that view. And we can also perform probability calculations by adjusting our bounds. So I can also do that by dragging directly in the view. And for argument's sake, we could imagine, for example, that we know that there's a very high risk of the vehicle tipping over if our maximum yaw rate exceeds, or the vehicle spinning out if our maximum yaw rate exceeds 29.5. So from looking at this plot, we can see that we're not going to exceed that value 98.6% of the time approximately, but that might be too much a risk given the severity of what could happen if you exceed that value. You could imagine other cases where maybe the consequence is less severe of exceeding that value, and you'd be happy perhaps to accept, that about 1.5% risk value associated with it. If we did determine that this percentage was, not high enough, that we need to be more around 99.9% sure we're not going to exceed the value, we need to make changes to our inputs, make changes to the distributions and the uncertainty associated with them that is going to tighten up this distribution so that we're closer to having 100% of the distribution to the left of 29.5. So one way to make that determination, which uses a SmartUQ tool we haven't had time to really cover much in this presentation, is we could have performed a sensitivity analysis using SmartUQ. So the sensitivity analysis would have told us which of our 10 inputs are most responsible for variability in the output. And by looking at that, we could, those inputs that are the most, those inputs that are the most significant to the output are going to be the ones where you're going to get the most bang for your buck in terms of if you can tighten the uncertainty around those, you're going to have the biggest effect on this distribution. So that's one way a sensitivity analysis can be used. It's to look at where of your set of inputs, which ones are you going to get the most value from in tightening your output distribution if you can make changes to those input uncertainties. So with that, I'm going to conclude the presentation. I just want to give a couple final notes just on different things and resources we have available on our website. So for one, we have a number of white papers available. A couple that might be of interest are a statistical calibration white paper and our SmartUQ Pushing the Boundaries of Engineering Analytics white paper. We also have a few webinars that are upcoming. So we have one on December 4th that's going to show a light weighting of a bracket using a simulation model with uncertainty quantification. And then we also have another webinar coming up in January that shows statistical calibration of a balloon expandable coronary stent. And some of our past webinars that are available on demand that might be of interest include a previous webinar we did with MSC. The previous webinar shows MSC Adams View integration with SmartUQ. So it's similar to this presentation, except the product and the example that we're highlighting is MSC Adams View example. So with that, I'd be happy to take any questions. Thank you for your time.
Thank you, Kevin. So we'll wait a couple of minutes for the questions to start streaming in. I see a couple. I see a couple that have already come in, Gavin. So maybe we can start off with these. The first one is a question on the emulator itself. So the question is, how is the emulator created? Is this just a response surface like in Adams Insight, or are we using some kind of a neural network to?
Okay. Yeah. So it's not a response surface model or a neural network. What we tend to use and what most of our technology is built on is a Gaussian process kringing models. And that has a number of advantages over something like a response surface method. The first is it's more accurate in its predictive ability. It requires less points to build to that level of accuracy as well. And really a main strength of our tools and our Gaussian process models is how quickly they fit the data set. So they can fit the data very quickly. There's also, as you saw, there's not a whole lot of settings required. So it's pretty hands-off to fit our emulators versus, you know, a response surface method might rely on regression methods. A neural network is going to require the tuning of a lot of different hyperparameters probably. So there's going to be a lot of manual decision making that has to be done by the user in order to get an accurate predictive model, and that's not the case with the emulators that we're using here. And there's also another really strong point of the emulators is that you don't need beforehand knowledge of the response shape or the response profile. So, if you're doing something that's based on a regression method, for example, a linear regression, you need to have some sort of inherent understanding the response is linear in nature. Otherwise, the method isn't going to work. And that's not the case here with our emulators. You don't really need to know that information beforehand, which means you can fit highly nonlinear response profiles and data sets that you have very little information on what the response shape should be.
Thanks, Gavin. The next question is on the number of data points required to populate the design space. So we used 100 data points. Is there a rule of thumb for how many points should be sampled to the design space based on the number of inputs?
Yeah, so the 100 points I used for the 10 inputs there follows what is considered the rule of thumb. So it's 10 points per input dimension. But that's a very rough rule of thumb. That's gonna vary a lot depending on a few factors. So one of the things that's gonna affect that is how accurate of a model do you need for your purposes. So if you need a less accurate model for your purposes, you're going to be able to get away with fewer points, for example. We have a few tools, given the fact that it's sort of, it's not a hard and fast rule. We have some tools built into SmartUQ that sort of help with building up your design of experiments and building your models without, having to commit too many runs up front. So if you have a simulation that takes a really long amount of time, you might not necessarily want to run 100 simulations from the get-go, when ultimately it might be the case that you only needed 30 or 40 or 50 to properly characterize your response space. And the response space, again, the complexity of that is another factor that's going to affect how many simulations you need to run and how big your design of experiments needs to be. So, one of our processes involves sort of unique DOEs we have that are going to split up the overall DOE into different chunks that you can sort of apply an iterative process to. So you could, run the first chunk from the DOE, which will inherently, because of how this is set up, be space filling on its own, check the accuracy. If the accuracy meets your requirements, that's great. If not, you bring in the next chunk and proceed in that fashion. Another nice thing about our emulators that I didn't mention in the previous question is that they provide, inherently the form provides variance information. So every prediction you make with one of our emulators doesn't just give you a prediction, it gives you a prediction plus a measure of uncertainty in that prediction. And that information can be leveraged in some of our other tools for augmenting your design. So you may build an emulator initially to have a specific number of points in it. You fit the emulator with that data, the accuracies and what you need. You could either use one of our tools to sort of add points purely in a space filling manner, just sort of increase the density of points within that design, and then run those points and fit your emulator with everything. But you can also use a process that, rather than just purely trying to fill out the space of the design, uses that information on the uncertainty to target adding points to the specific areas of the design space where the emulator is has the most uncertainty. So you're trying to target to best improve the uncertainty. And we even have a newer tool that sort of automates that whole process. So you essentially assign a target accuracy, and the tool continually keeps intelligently adding points to the design of experiments, calling out to Adam's car, asking Adam's car to run the points, bringing the results back into SmartUQ, assessing the accuracy, and then repeating if necessary. So again, to sort of sum up, there is a rule of 10, 10 points per input dimension, but it can vary. What is actually required can vary greatly between that. So as a result, we basically offer a bunch of different tools that allow you to iteratively build up, or to not have to run too many points initially in building your emulator.
Okay, makes sense. So there's a question on how would Smart communicate with other modeling software? So there's a user who currently has a modeling application that uses a Python API. How much effort would it be to connect SmartUQ via the API?
Yeah, so I mean, actually, we have a API for SmartUQ, which is a Python API. So if you have an existing workflow that's written in Python and that is calling out to a simulation tool from Python, it would be really easy to incorporate our tools into that. So using our Python API within that, you could create design of experiments that you would then send to your simulation tool. The simulation tool within, your Python coding would send back the results, and then you could, using our Python API, directly build emulators with those results, and then make predictions and perform all the analytics we discussed within our Python API. So that's a pretty straightforward thing to do using SmartUQ's tools.
Okay, that makes sense. So there's a question about, so typically in vehicle design, use a lot of these subjective metrics for things like gauging the quality of a ride, to gauge the comfort. So is there a way to take these subjective parameters, right, and relate them to objective metrics and utilize them for uncertainty quantification?
Yeah, definitely. So the emulator that I showed in the webinar today is sort of our, the base tool upon which everything else is built. All of our different emulators are built. So we have a number of different emulators that we've developed to handle specific challenges that customers, for example, have had. And so, yeah, there's a lot of emulators to handle different types of data than the sort of continuous data we've looked at in this problem. So you could certainly do that. So we have one emulator that, rather than just taking continuous inputs, can also handle discrete or categorical inputs. So if you had some sort of measure of, ride quality, and it was, smooth, rough, or, something to characterize in between, that could definitely be one of your inputs within the emulator you're building in SmartUQ. And then your output can be, whatever you're concerned with. So yeah, that's definitely something that can be done. You could also, if you had a numerical scale, a 1 to 10 scale that describes the ride quality, of course, that could be an input as well. That's still sort of discrete values, but we have variants of our emulator that can handle that.
Okay, makes sense. Yeah, it looks like we have covered all the questions, Gavin. Thanks again. It's a great presentation, very informative. And thanks everyone for attending. If you have any other questions, please reach out to me or Gavin. And we'll be continuing to integrate with SmartUQ. So Adams will be integrating more and more with SmartUQ, and as that happens, keep all of you informed. And we'll definitely have follow-up webinar sessions to talk about those integrations. So with that said, I am going to stop the webinar, and thanks again everyone for attending. Thanks, Gavin.
Thank you.